Hello, and welcome to Lesson 18 of this Introduction to Differential Equations with Wolfram U. In this lesson, we will discuss solving second-order differential equations where singular points are present. We will then examine specific equations of this type, known as Euler equations, and look at the behavior of the solutions of such equations when the roots of the associated quadratic polynomial are distinct, repeated, or complex. Let's take a look at an overview of this lesson. In the previous lesson, we studied second-order differential equations with functional coefficients that took the form of polynomials. We found solutions by constructing a Taylor series about an ordinary point, then found the coefficients for that series such that the expansion satisfies the differential equation around the ordinary point. A point x0 is an ordinary point when the function p evaluated at x0 is not equal to 0. In the previous lesson, we divided the equation by p of x to get the differential equation into a form suitable for solving, so we wanted p of x0 to be non-zero so that the coefficients of y and y prime were analytic about x0. This lesson will consider solving differential equations with singular points, that is, where p of x0 is equal to 0. We will then examine a special class of these types of equations known as Euler equations, which take the form given here. As we will see, the behavior of solutions to Euler equations will depend largely on the power of x in the solution. This is shown in the plot here for some powers of x. The behavior of the solution is seen to be very different for large and small values of x, depending on the power. Euler equations are linear second-order differential equations that take the form here, with alpha and beta being real numbers. Euler observed that the differential equation can be simplified by assuming the solution is some power of x. The differential equation is unsimplified when substituting this form into the differential equation and using the power rule from calculus. This is analogous to when we encounter differential equations with constant coefficients and assume that the solution took the form of an exponential in order to find the characteristic equation. In a similar way, assuming that the solution to Euler equation takes the form of x to the r and substituting this into the differential equation gives a quadratic in terms of r. The values for r that are roots to the quadratic equation will be solutions to the differential equation when used in the exponent of x to the r. As was the case when using the characteristic equation in previous lessons, the behavior of the solution will change depending on if the roots are real and distinct, repeated, or complex. On the previous slide, we assumed the solution to Euler equations would take the form of x to the r and substituted this form into the differential equation to get this quadratic equation for r. If this quadratic polynomial has two distinct roots, r1 and r2, then there are two solutions, x to the r1 and x to the r2, since these are the two functions that will solve the differential equation given these roots. Take a look at the Wronskian for these two functions. It is seen that the Wronskian is non-zero for all positive values of x because we have assumed that the two roots are distinct, which is to say that r1 is not equal to r2. Therefore, we have formed a fundamental solution set to this differential equation. Since the general solution is a linear combination of the functions which form the fundamental solution set, we can insert the arbitrary constants and write the general solution for positive x values as this. Let's solve the Euler equation given here. Assume the solution is of the form x to the r, and substitute this form into the differential equation to get a quadratic polynomial for r. Therefore, when 6 plus 5r plus r squared is equal to 0, x to the r will solve the differential equation. The roots can be calculated with ease in the Wolfram language. It is seen that the two solutions to the differential equation will be x to the minus 3 and x to the minus 2. The general solution will be a linear combination of these two individual solutions. This result can be confirmed with the solved value. As expected, the result from d-solve value is a linear combination of the x to the minus 3 term and an x to the minus 2 term. When the roots are repeated, there is only one solution for x to the r that can use that root. When we solve second-order equations with constant coefficients and the roots to the characteristic equation were repeated, we needed to find a different functional form to represent the second solution. In that case, we used the method of D'Alembert, where we assumed that the second solution was some arbitrary function u of x times our assumed form for the solution. We then substituted this form into the differential equation to find what u of x needed to be to satisfy the differential equation. When solving Euler equations with repeated roots, we can apply an analogous method. In this case, we will again assume that the second solution to the Euler equation takes the form of u of x times the assumed form for the solution, x to the r1 in this case, where r1 is a root to the quadratic polynomial. Substituting this form into the differential equation, we can show that u of x is equal to natural log of x. Looking at the Wronskian, we see that the Wronskian is non-zero for all positive values of x. Therefore, we have found a fundamental solution set to this differential equation, with the general solution being a linear combination of these two functions. Consider solving the Euler equation here. Substituting in x to the r as the solution gives a polynomial which can be solved for r. There is only one root to the equation, r equals minus 3. Therefore, the roots are repeated since there is only one of them that solves the polynomial, so we know that the other solution must take the form of natural log of x times x to the r. This result can be checked with d-solve value. The general result is seen to be a linear combination of the first solution we found, x to the minus 3, and the second solution we found, natural log of x times x to the minus 3. Now let's consider the last case, which is where the roots of the polynomial are complex. In this case, the solutions will take the form of x to the a plus or minus ib. Using the properties of logarithms and exponential functions along with Euler's formula, we can write this expression in terms of cosines, sines, logs, and powers. Therefore, we have found two solutions to the differential equation given here, one in terms of cosine and one in terms of sine. By taking a look at the Wronskian for these two solutions, we see that it is non-zero for all positive values of x as long as b is non-zero as well. However, b must be non-zero since x to the a plus or minus ib would not be complex if b were zero. Therefore, we have found a fundamental solution set, with the general solution being a linear combination of these two functions. Let's solve the Euler equation here. Assuming the solution takes the form of x to the r, substitute this form into the differential equation and simplify. Whenever this polynomial equals 0, x to the r will solve the differential equation. Calculating the roots, we see that the roots are complex. Therefore, the solution must take the form we found on the previous slide, using minus 2 as the real part of the root and square root of 2 as the imaginary part. This result can again be confirmed with d-solve value. When solving Euler equations, we had to consider if the roots of the polynomial we encountered had distinct, repeated, or complex roots. If the roots were distinct, we got a linear combination of x to the r functions, with the two roots in the exponents. If the roots were repeated, the second solution included a natural log term, while if the roots were complex, we got a more complicated form involving powers, cosines, sines, and natural logs. A main contributing factor to the shape of the solution will be the value of the power in the exponents. We can see in the plot the behavior of various powers for positive values of x. For negative powers, such as x to the minus 3 and x to the minus 1/2, the solution diverges near x equals 0 and goes to 0 for larger values of x. For powers between 0 and 1, such as square root of x, the solution goes to infinity as x goes to infinity, but rather slowly with increasing x. As the exponent gets larger, the solution grows faster for values of x greater than 1. Let's take a look at the qualitative behavior of each type of solution in a little more detail. When the roots are real and distinct, the solution will take the form given here as a linear combination of x to the r functions, with the two roots being the values of the two exponents. Solutions of this form will converge to 0 for large values of x only when both of the exponents are negative. If either of the r1 or r2 are positive, the solution will diverge for large values of x. This is the type of solution we found in example 1. Using limit, we see that the solution does indeed converge to 0 as x goes to infinity. When the solutions have repeated roots, we saw that they will take the form given here. Therefore, the solution will only converge to 0 for large values of x when the single repeated root is negative. This can be shown using limit. This is the type of solution we found in example 2. Plotting the solution with the arbitrary constants both equal to 1, we see that the solution does appear to go to 0 for large values of x, while it goes to infinity as x goes to 0 due to the negative exponents. When the roots are complex, the solution will take the form given here. While the solution is more complicated when the roots are complex, the qualitative behavior is once again largely determined by the value of the power in the exponent x to the a. This was the situation in example 3, where a was equal to minus 2. We can obtain this result again using d-solve value. The solution will largely be determined by the 1 over x squared term. This can be seen by plotting the solution when the two coefficients are equal to 1. We can see that the solution goes to 0 for large values of x. The magnitude of the solution will go to infinity as x goes to 0, but due to the cosine and sine terms along with the log term going to minus infinity, the sign of the solution will oscillate between positive and negative values. In this lesson, we examined solution methods for a particular class of second-order differential equations known as Euler equations. These are equations that take the form given here. In this lesson, we were able to determine solutions for any value of the constants alpha and beta. The general solution took three different forms depending on the properties of the roots. If the roots were distinct, they would take the form given here, where the exponents contain the two distinct roots. If the roots were repeated, the second solution would contain a natural log term, while the exponents would both contain the repeated root. If the roots are complex, then we get an x to the a term that largely determines the qualitative behavior of the solution, multiplied by terms involving cosine and sine, with natural logs as their arguments. In the next lesson, we will see how the Euler equation plays a crucial role in finding solutions near a singular point.